Hey, hello and welcome back everybody. So we are here on section 1.4, common rules of the continuous integral, and you probably recall in the previous video I did cover this table of integral rules, which I've included at the beginning of this section, and we're actually going to spend three days on this this section of common rules of the continuous integral, mostly because this is the beginning of the section of Calculus 2 that most students really have a hard time with. It's kind of one of the reasons why Calculus 2 is notorious for being a difficult class, and I want to express the reason why. The reason mainly is because it is very tricky to know when to apply either of these. And moreover, which functions to choose for f and or g. Right, in both cases we kind of have these functions f and g, or f multiplied by g, and it's quite tricky to know. I mean, in some cases you'll see this multiplication occurs in both cases, so it's tricky to know which of the two cases you may want to use, and even more tricky to know, even if you commit to use substitution, you commit to integration by parts, specifically which functions f and g within kind of a larger collection of terms in the integrand you actually want to choose to get a useful answer. And so what we end up doing, and this is why we're spending 3 days on it, is we need to be able to do both of these very quickly in our heads. At the very least start them. To start these very quickly in our heads. And it's this juggling of multiple integration techniques with multiple choices of f's and g's, all more or less in one's head, because you just eventually run out of time and or effort if you can't juggle them all in your head. So you have to juggle basically every possible case at once, and then by juggling it you can see which one, if you go ahead and start them quickly, you end up seeing which one actually improves the problem for you. And so that's really the intuition that's tricky in Calculus 2, and something we're going to spend at the very least our third day when we're tackling this section on the intuition. So the primary schedule for the next 3 days will be, we're going to spend today on use substitution, the next day on integration by parts, and then the third day on some form of a intuition to actually figure out when we should use those. Unfortunately, this only scratches the surface. We're going to take a break away from integration techniques for a little while, but this does actually only scratch the surface with regards to Calculus 2 integration techniques. We will encounter more integration techniques eventually, so it doesn't even get easier from here, I have to say. I mean, we take a break, so in some ways it gets easier for that break, but we'll eventually get back to more integration techniques, and that won't be fun. I mean, it's fun for me, but it may not be fun for you. So let's get this actual subsection started, which is integration by U substitution. And many of you probably saw this in a Calculus 1 course. It's usually one of the very last subjects covered in a Calculus 1 course. In many ways, integration by substitution is the opposite of the chain rule. And so let's just recall the chain rule real quick. If I take a derivative of a composition of functions, this is where I have one function inside of the other, the output is a derivative of the outside function, and then we preserve the inside function, then we multiply by the derivative of the inside function. Now all that means is if I decide to reverse this, and reversing in this case would be to get rid of d dx on the left hand side and include an antiderivative or an integral on the right hand side. If I'm going to reverse this, then what I need to find inside of my integral is, well, a function who I can easily take an antiderivative of, right, because there's f prime on the right and it turns into f on the left. So some function I can take an antiderivative. As well as a function inside of that, so that's going to be my case g. So there's going to be some function g inside of the function, which is easy to take an antiderivative of. But even more than that, we need to multiply by the derivative of what's on the inside. Multiplied, and this is from the beginning, right? It needs to be multiplied by the derivative of what we call the inside function. So if we don't see that multiplication by the derivative of the inside function, tough luck. So that's what we'll be encountering today. The way it's often called integration by substitution, or in particular integration by U substitution, is because we give this inside function the new name U. So we name this the variable U, and in fact we name kind of the entire term g prime dx. We name this the variable, or the differential technically, the differential du. And so you end up with something of the form integral f of u du, which now makes it clear we're just integrating that particular function f and then substituting the gx back into it at the end. So I do go through this in the step-by-step process as part of this proposition. So I say equivalently, the integration is actually performed with the following step-by-step process. We're going to search the integrand for two things: a function within parentheses, which we'll call g of x for now. You can also call this u, right? That's the point of u substitution, as well as a multiplication by its derivative, which should look like, some true multiplication, and then a g prime. So whatever the derivative of that inside function is, ideally it's actually showing up in the integral. That's usually not the case, and we're going to encounter those cases later where you can't really see g prime. Sometimes you have to get lucky. But in some of the more straightforward u substitutions, g prime should be right there for you. What we end up doing, and I kind of mentioned this already, is we're going to define the new variable u. There I use my defined equal sign, right? Because it's up to us to define that. We're going to define u to be equal to that inside function. And then that differential of u, if you go through the process of actually computing a differential, truly does become g prime dx. And so we do end up with the integral, right? In step 4, integrate now with respect to the variable u, we do end up with the integral f of u du, which ideally we can find an antiderivative of, which I'm calling capital F. And then in step 5, we perform the reverse substitution where that u actually ends up being g of x. And so our solution is f, capital F, some antiderivative of g of x plus c. So that's a step-by-step process. I'm not going to go through the proof, but I will go through an example of what I'm calling a trivial substitution. And this is where, like I said before, it's quite straightforward where our derivative of the inside function appears. And we don't kind of have to go through extra work to force it to appear. So in this case, we got the integral, or the antiderivative, of sine of x squared minus 3x plus 1, and we're multiplying that by 2x minus 3. And so it should be fairly straightforward. We're looking for parentheses and functions inside of parentheses when it comes to u substitution. Here's some parentheses. There's really two copies of parentheses, but the second set is being multiplied by terms. And so there really is this one function in parentheses here inside of another function. It's inside of sine here, x squared minus 3x plus 1. And since that's inside of sine of x, it's a good idea to label that g. And we should go ahead and calculate the derivative. What would the derivative of x squared minus 3x plus 1 be? Well, the power rule says take that 2, put it out front. We're getting 2x minus, well, the derivative of x is just 1, so 2x minus 3, and the derivative of 1 is 0. And so g prime of x ends up being 2x minus 3, which, lo and behold, is exactly what we have multiplied everything by, which means we can represent this as the integral of sine of g of x times the derivative of g of x dx. And it makes it quite clear that we want to choose this g of x, or x squared minus 3x plus 1, as our variable u. So let's actually go through the steps here. There I've labeled u, x squared minus 3x plus 1, and we already know its derivative is what's multiplying things, so 2x minus 3. If I want to think about it as differentials, its du is 2x minus 3 dx. And so I'm going to perform the substitution where this gets thrown in for x squared minus 3x plus 1, so I'm just writing that now as sine of u, and my second term for du is getting thrown in as 2x minus 3 dx, so I'm just going to replace that with du. We end up with the integral of sine of u du, or in other words, the antiderivative of sine, which we can go ahead and look at the table, or we can memorize these formulas for the antiderivative of sine. It's negative cosine, and because we're integrating in the variable u, it's going to be negative cosine of u, of course, plus an arbitrary constant c. At the very last step, we're going to perform the reverse substitution, which means we're going to replace now u, since that was a variable I integrated in, with our original function of x, in this case x squared minus 3x plus 1. And under making that substitution in u, we end up with negative cosine x squared minus 3x plus 1 as our antiderivative, but of course there's a plus c that's hanging around. So that's kind of the most basic, straightforward version of u substitution, where that derivative of the inside function is screaming right at you and saying, hey, I'm here, you don't have to worry about me anymore. Kind of the trickier u substitution terms, and really where calculus 2 makes your life a little more difficult, I'm going to introduce this step-by-step process for it, and then we'll see some examples. So the step-by-step process for what I'm calling non-trivial substitutions is we're just going to have to make a guess. So I'm calling this guess a substitution candidate. And what we're going to want out of it is that it's a function within parentheses, or a function within another function, right? There may be multiple of these, which is what kind of makes it tricky sometimes. You just kind of have to take one of them and run with it and see what happens, and then give yourself the opportunity to admit you were wrong if something doesn't work out, and then go back to the beginning and try again. So we're going to search for a substitution candidate, which is most often this function in parentheses, and we're just going to go right ahead and define u to be equal to that substitution candidate. Now, the derivative may not appear in the problem, and that's okay. But what we can do, even if the derivative doesn't appear in the problem, is, well, let's think about what this formula means. U equals g of x when it comes to inverse functions. This is kind of why we spent some time studying inverse functions earlier, is that actually the definition u is equal to g of x, so long as g is invertible, is equivalent to the definition x is equal to g inverse of u. And so I'm basically pulling that g to the left-hand side. I'm going to push it on top of u instead, but now it looks like a g inverse. And so what this is telling me is that I can actually substitute every copy of x in my integral with the inverse function of my substitution candidate. And this even occurs for, I haven't talked about what should du equal, right? Question mark. We actually don't know what it'll equal in the non-trivial cases. We don't worry about what it equals. Instead, we worry about what dx, which has always been in the integral. This will always be in the integral. So we always have a dx. Well, you can always compute dx in terms of du. It ends up being, if you go through kind of the differentiation aspect of everything, it ends up being whatever the derivative of g inverse is and then multiplied by du. So we need to take a derivative in the variable u of g inverse of u. That's going to give us dx. Now, in some cases, that will perfectly cancel, with the g prime term that was already there, but in other cases, it may not perfectly cancel. So then in step 3, we go ahead and do actually replace all instances of x with g inverse of u. And in particular, the one case, g of x will indeed be replaced as g of g inverse of u. In other words, we're replacing g of x with u, just like in the trivial setting. But the trickier term is here over with dx. dx gets replaced with that derivative of g inverse and then multiplied by du. And so that's the non-trivial setting. At this point in step 4, we need to simplify as much as possible because this is the point at which we find out if we made a good or bad choice. Here is where we find out if our choice worked. Because if we simplify as much as possible, here I say we hope that the resulting integral may be found. So if you look at that integral and you say, oh, I actually know how to take that antiderivative now, then you're good to go. But in a lot of cases, it's not going to be the case. So I say if it's not possible, either a poor choice for u was made or the integral cannot be solved with substitution. So it's going to be a lot of cases where we unfortunately just cannot solve an integral with substitution. We have to use some sort of other technique. There's not really a good way to tell which one of these is the case until you try it and you fail, and then you try something else again, and you still don't know if you'll eventually reach it. I mean, the integral may not be possible to compute at all. Of course, on an exam, it will be, but aside from that, we don't actually know the future of these integrals without trying infinitely many options and then running into brick walls or eventually getting lucky. And so there's this real intuition that needs to be developed throughout this semester to finding these antiderivatives. So we're going to try to get lucky in step 4, and then if we think we can get lucky and we've taken the antiderivative, we're going to go right back to that very same step 5, even in the trivial cases where we just replace all instances of u, the variable that we've switched to, now with gx, the original substitution. So let's see what this actually looks like. Here's a lovely example of a non-trivial substitution. What do I have here? I've got an x plus 2 in the numerator and a cube root of x plus 3 in the denominator. Let's just notice right away that there is no derivative of an quote-unquote inside function here, right? Even if, and we jump down kind of to step 1 here, even if we rewrite this cube root of x plus 3 as parentheses x plus 3 to the 1/3, or even x plus 3 to minus 1/3 if we want to pull it out of the denominator, the derivative of x plus 3 is just 1. And so, yeah, I mean, technically we've gone ahead and multiplied by the derivative of that, but there's that numerator x plus 2 that's sitting around that is not equal to the derivative of x plus 3, my inside function. We will be able to compute this antiderivative if we make that substitution x plus 3 equals u. So to see that actually happen, let's go ahead and make that choice for the substitution candidates. We're going to call g of x x plus 3, or rather g of x, which is the same as u, x plus 3. We have to invert this, right? And invert, when it comes to this case, it simply means solve for x, right? So, using this notation g inverse maybe is a little bit intimidating. All I actually mean is to look at this u equals x plus 3, and we're going to solve it for x. Well, to solve that for x, we have to just subtract 3 from both sides. We end up with x is equal to u minus 3. And so that tells us that when we make our substitution, we're just going to replace each x with u minus 3 when it comes to our substitution. And that should simplify things a little bit for us. The only tricky part is saying, okay, there is a dx term here. What do we do with dx? Well, let's think about it. We can replace x with u minus 3, so we're really taking du minus 3. This is just me replacing that x and dx with u minus 3. Well, what is du minus 3? It's the derivative of u minus 3, which happens to be 1 times the differential in the u variable. And so in this case, we get a little bit lucky. Dx and du are actually the same thing. So if we go to our original integral then, which was this, integral x plus 2 over x plus 3 to the 1/3 power dx, and we look at it down here, we're going to replace every x. So there's 1, 2 x's there. I'm going to replace those with u minus 3. And that's what they look like, u minus 3 and u minus 3. And I'm going to replace the dx on the right-hand side here, and replace that with du. So I go ahead and replace that with du. And I end up with the following integral, which is given here, but of course this is at step 4, moving on to that step 4, where I say we have to simplify as much as possible. If you ever got tired of simplifying in pre-calculus or calculus, this was the reason why it was so stressed, because you can't actually tell if a specific function is readily integrable unless you simplify it, or at the very least rearrange it into a form that makes a little bit more sense. And so in this case, what are we going to do? Well, our denominator, the 3's cancel each other. That's kind of why we made our original substitution choice. And in the numerator, we've got a minus 3 and a plus 2, which themselves can combine to give me negative 1. Now let's think about our denominator now. Our denominator is simplified to u to the 1/3. And so there's no longer an addition in the denominator, right? These additions are kind of what makes your life hard when you're trying to distribute denominators. You can't really integrate denominators that way. But now that it's only a single term, it can distribute to both terms in the numerator. And when it distributes to both terms in the numerator, first term is u over u to the 1/3, second term is 1 over u to the 1/3. If I simplify each of those, first term is u to the 2/3, second term, negative u to the negative 1/3. And both of these are integrable using the power rule, which, if we forgot what the power rule is, because I didn't really cover it, it ends up being the integral of x to the n, or I guess in this case u to the n, but I'll just keep it as x here. Well, you take, instead of subtracting 1 from the power like in a derivative, you're going to add 1 to the power, and we're going to divide by that new power. We're going to add c to it. So that's our power rule for integrals. We can apply that to both cases of u. In the first case, 2/3, we're going to add 1 to that power. We're going to divide by the new power. Same in the second case, negative 1/3, we're going to add 1 to that power, divide by the new power. And so the first power turns out to be 5/3. We're dividing by 5/3. The second power ends up being 2/3 divided by 2/3. If we simplify a little bit, 3/5 u to the 5/3 minus 3/2 u to the 2/3 plus c. So we were able to simplify and integrate this. And then our very last step is to perform the reverse substitution, where I know both of these u's can actually be written in terms of x, in this case x plus 3, so I'm just going to make that substitution for both u's. I end up with 3/5 x plus 3 to the 5/3. Should be a minus here. Little typo, minus 3/2 x plus 3 to the 2/3 and plus c. So that's going to be my antiderivative here. That non-trivial substitution is a little bit tricky, and we just have to get lucky. I mean, you could have imagined maybe I made the poor choice and decided to choose x plus 2 as my substitution terms, and that just wouldn't work in this case. So we have to get okay, just kind of having some intuition about what's the better function to try to substitute. We also have to be willing to give up sometimes, but that's something we will see in the intuition section that's coming up in a bit. Let's look at another example of a non-trivial substitution. Here we're going to compute the antiderivative of 1 over e to the x plus 1. And currently it doesn't really look like there are any functions in parentheses, but let's always recall that denominators can be written as negative exponents, or negative to the negative powers. And so if we put parentheses around e to the x plus 1, we can write it as to the negative first power. And then lo and behold, we do have a term in parentheses, which we're going to go ahead and choose as our substitution candidate. In other words, I'm going to define u to be equal to this e to the x plus 1, even though it's derivative, right? What is the derivative of e to the x plus 1? Well, that would be e to the x. dx is really nowhere to be found here. We only have a dx. Only a dx, not e to the x dx. So that's kind of worries us. It says, well, maybe this might not work because I don't see its derivative, but we might as well try in this non-trivial setting. And so when we make this definition, we do have to perform that inversion, which as always just means solve for x. So if we solve for x here, we're going to subtract 1, and then we're going to compute the natural log, right? Because I've got this e to the x here, and I would like to solve that for x. The whole point of the natural log is to cancel with an exponential, specifically of base e in the natural log setting. So we have that x is equal to the natural log of u minus 1. And at this stage, we can actually compute what dx should be equal to, because we just go ahead and perform a derivative of this natural log u minus 1 in the u variable, right? And there it is, natural derivative of natural log u minus 1 in the u variable. We can use our natural log rule for derivatives here. We end up with 1 divided by u minus 1 as the dx term. So what does that mean? That means we're going to replace every x in our original expression with log u minus 1, and we're going to replace every dx in our original expression with 1 divided by u minus 1 du. If I go ahead and go through the work of that, here was my original expression, 1 over e to the x plus 1. I'm replacing x with log u minus 1, so I'm getting e to the log u minus 1. And I'm replacing every dx with 1 over u minus 1 du, and so there's my dx getting replaced, 1 over u minus 1 du. If I go ahead and simplify, right, that's the whole point of step 4, is simplify this integral as much as possible. Well, the whole point of the e in the natural log is that those cancel, so I end up really with a u minus 1 plus 1 in that denominator, so those minus 1s and plus 1s can cancel, and I'm just multiplying by this other fraction, 1 over u minus 1. And so every term is going to multiply together. I end up with 1 over u times u minus 1. Now this next step is going to feel foreign, right? Because something like 1 over u times u minus 1, you may ask yourself, is this integrable? The answer is yes, but we haven't necessarily studied the technique that will tell us the answer is yes. And so if this problem shows up in homework, if this problem shows up on a quiz, etc., I will tell you at this stage, in a hint, I'll say something along the lines of, hint, 1 divided by u times u plus 1 is actually equal to kind of two fractions split from each other, 1 divided by u, or really negative 1 divided by u, plus 1 divided by u minus 1. If you go through common denominator and simplify that sum of fractions there, you do in fact end up with 1 divided by u times u plus 1. We'll experience that later. It's called partial fraction decomposition to actually go through the work to see why that's the case. But for now, take it as a hint, something I would provide to you if you were experiencing this problem. And then when we look at both of these individually, these are both integrable. Maybe you're a little bit questioning me on the second case of 1 over u minus 1, but it's just a natural log integral with a single, one more substitution, right? You can substitute that denominator, u minus 1, divided to be equal to w or something. You have 1 over w dw. So these both actually integrate using the natural log. And if you go through that work, what do we get? Well, you have a negative sign in the first case, 1 over u, the antiderivative of that is the natural log. And let's just remember that from our power rule. U to the minus 1 du is natural log, absolute value u plus c. This is our power rule, specific to the power negative 1. Negative 1 there. So we get a negative natural log of u in the first case. Like I said, it's one extra step of substitution to really give that denominator u minus 1. The variable name, maybe w is equal to u minus 1, and then dw is equal to du, and so this ends up being 1 over w, in other words, log of w, and then perform your substitution again, you get log of u minus 1. So these are both integrable, and if we go ahead and use a log rule right here, let's think about how the log rule is working there. Well, I actually have a log u minus 1, and then it's minus log of u, so in other words, divide inside terms, but just make sure that it's the negative term is the one in the denominator, so that's the u in this case. So we put a u in the denominator, and we can simplify that a little bit. Now, the reason why I've combined those is because they end up simplifying in step 5, where step 5 is where I replace all instances of u with its original definition, e to the x plus 1. So I'm just going to replace both this u and that u with e to the x plus 1. There and there, e to the x plus 1. What do I get in my numerator? Well, the plus 1 and the minus 1 cancel. The denominator remains as a plus 1, and so we end up with log of e to the x over e to the x plus 1. And if I go through a little bit of work doing the reverse log rule, right, because there's a division on the inside of the log, so I can swap that around for a subtraction outside of the log. This is useful because at least one of my terms will cancel with a log and an exponential, and I'm just left with x in that first case, minus log of e to the x plus 1 plus c. So that's another example of a non-trivial substitution that we just want to get used to. You know, if I'm providing an integral for you, odds are like the most expected term function on the inside of the integral, it is going to be the one that works for a non-trivial substitution. I'm not going to try to confuse you or give you the wrong result. And this does get tricky when we eventually encounter integration by parts, and I'm going to expect you to make the choice between integration by parts and substitution. But in general, if you make the choice on substitution, kind of the first substitution candidate you see in the problem is probably the case that's going to work out for you. The next section, I have a remark here where this is my opinion. It's not something you have to follow. Everything else, of course, is kind of mathematical fact. But my opinion is to avoid trying to adjust the bounds when using u substitution on definite integrals, right? Definite integrals, if we recall, these integrals where we have some minimum value and some maximum value, they're calculating an area for us. Maybe I've got f of g of x times g prime of x dx. Well, we know that that antiderivative of this is some capital F of g of x. And then because it's a definite integral, I can evaluate at the bounds x min and x max, or in other words, f of g of x max minus f of g of x min. So if you're going to compute this, I often say, you know, if you get through, you may have learned in the past, you get to a point where you make this substitution, f of u du. If I'm going to substitute, u equals g of x. In the past, it's a lot of cases, you would go through the extra work to calculate u min and u max, and these were, you know, calculated really as what you would expect them to be calculated as, which was u max equals g of x max, and u min equals g of x min. And it's just one extra step that I personally don't like doing. In my mind, what I always do is I will convert these problems, and this is really what I'm saying in the remark, I convert these problems to an indefinite integral first. So when I perform this substitution, I just leave the bounds open, which means this is now going to be an antiderivative, not a definite integral. And I just go ahead and compute that antiderivative using antiderivative rules. I get some capital F of u, which I then send over to capital F of g of x. And then I jump back and I say, by the way, I did actually originally have some bounds, and I just evaluate on those bounds. So rather than necessarily shoving bounds in, even when you translate to u, I kind of use u as this intermediate step, but then I translate everything back in the variable x, and I don't worry about changing to the variable u. However, if you want to change your variables u, right, we've got u min as gx min, u max is g of x max. So it's perfectly allowable. If that's what you learned, that's what you like. So I do have one example where it's basically to adjust bounds or not to adjust bounds. I go through it both ways and I show that we get the same answer. So let's look at the definite integral. So definite because I've included bounds here, -1 to 1, of x e to the x squared minus 1 dx. I'm going to start with my approach, which is the one where I don't adjust bounds. So I just immediately say, let's forget about the definite bounds being -1 and 1. So I've opened up my bounds and I'm just looking for an antiderivative here. Once I find our antiderivative, I can go ahead and compute f of 1 minus f of -1. That's how we would compute the definite integral. So with that said, let's find a substitution candidate. This one's really not as bad as our previous cases. If I look at what's in quote-unquote parentheses, right, up in the exponent there, that's really in parentheses. I've got an x squared minus 1. If we think about its derivative of x squared minus 1 is 2x, and so I don't quite have a 2x out front, but I certainly have the x term out front, so I'm getting pretty darn close. So I'm just going to go ahead and let x squared minus 1 equal g of x, which happens to also be my substitution candidate, so I'm going to let that be equal to u. Then we compute du by taking a derivative in the variable x, which I already kind of said was 2x. Well, my original expression only has an x in it. Here I've got a 2x. If I say du is equal to 2x dx, I could just go ahead and divide both sides by 2 and really say du over 2 is equal to x dx, which was in my original problem. So let's replace the term x dx in the original problem with 1/2 du, and we'll replace x squared minus 1 with u. So we do that there, x squared minus 1 becomes u, x dx becomes 1/2 du. And so we end up with just the antiderivative 1/2 e to the u du. Well, the exponential rule says the antiderivative of e to the x dx is just itself. And so we're just going to get 1/2 e to the u plus c out of this, and then I can jump back and say, oh, I originally made the substitution u was x squared minus 1, so I'm going to replace u with x squared minus 1. I get 1/2 e to the x squared minus 1 plus c. So this is my antiderivative, and now that I found an antiderivative, I can just evaluate these on the bounds and compute my definite integral. So there's my antiderivative. I'm just going to go ahead and evaluate this for the definite integral from -1 to 1. Evaluate it at 1 and subtract evaluating at -1. If I plug a 1 in for x, I get 1/2 e to the 1 squared minus 1 plus c. And I'm going to subtract plugging a -1 in for x, which is 1/2 e to the -1 squared minus 1 plus c. If I simplify those expressions, of course the c's always cancel. This is why you're not really forced to include c's on definite integrals. But the e's, right, we've got e to the 0 in both cases because this is 1 squared minus 1, -1 squared minus 1. These are both 0 and 0, so it's e to the 0. And they both end up being 1/2 times 1 plus c minus 1/2 times 1 plus c. Everything cancels, and you exactly get 0 as really the area under this curve. So that's me doing kind of my version where I like omitting the bounds right away, just finding an antiderivative and then throwing them back in there at the end. But if you want to go through the work of actually computing the new bounds in the variable u, let's actually go through that and I'll show you. It's basically equivalently difficult, but it's just one more thing for me to think about that I usually try to forget. So in this case, we're going to make the same substitution, right? U is equal to x squared minus 1, but let's recall our original integral, -1 to 1, e to the x squared minus 1 times x dx. I mean, I've swapped my x to the other side there. This was our integral. And with regards to substitution, everything stays the same. We still got du is equal to 2x dx. I can go ahead and divide both of these by 2 to say that really 1/2 du is equal to x dx, which is the term in my integral. So I'm going to replace all of those terms just like I did before. My integral x e to the x squared minus 1 dx becomes, e to the x times 1/2 du. But let's go ahead and talk about swapping bounds. So this 1 and -1 need to get swapped. Well, I have that 1 is equal to x max, and I also know that, well, u is equal to x squared minus 1. So that means u max is x max squared minus 1. In other words, it's equal to 1 squared minus 1. U max has to be equal to 0. So I'm going to replace the x max with u max, which happens to be 0. Same idea for -1 as x min. I'm just going to plug that in to the definition of u min for x. So x min squared minus 1. Well, x min was -1, and we square it, subtract 1. Turns out u min is equal to 0, which means I'm replacing x min with 0 when I make my substitution. At this point, now I'm only computing the definite integral in the variable u. Perfectly acceptable, but now I just go ahead and compute my antiderivative here. Nice little typo, that should be 1/2 out front. We compute the antiderivative of e to the u du. Well, it's still just e to the u, so I've got 1/2 e to the u with my definite bounds of 0 and 0. And of course, it's pretty clear at this point when the definite bounds are the exact same number. Of course, the two terms which I compute in the antiderivative are going to cancel each other, and my answer is still 0. So this just shows you that in either case, no matter which one you want to do, if you want to convert back to the variable x and put the original bounds in, you get 0. Or you do want to convert your bounds to the variable u, you still get the same answer. Anyway, that's all I've got for today. It's been a good day. I hope it feels fairly familiar with u sub. Those non-trivial terms, a little bit different, but definitely something that's useful because clearly they did work in both cases. Anyway, I'll see you in the next one where we're covering integration by parts. Look forward to that. Bye.